continue our conversation about exponential functions with a base other than e. And actually, we talked about exponential functions and logarithmic functions with bases other than e. And in the first video, part 1 in this section, we talked about the derivative of both of those functions. Now I want to speak about the integral of both of those functions. And let me remind you, when we have the integral of e to the x dx, it is just e to the x, right? Now, if you have something other than x up there, like for example e to the 3x dx, you would have to use a u substitution. So you would let u equal 3x. The derivative of that is 3 dx. And then you look over here and you go, I don't have a 3. So you put a 3 inside. So now you have 3 dx, but you have to put a 1/3 in front to compensate. And that gives you 1/3 the integral of e to the u. And then remember the 3 dx is du. And then you just use that same rule. That's 1/3 the integral of e to the u. Not integral. The integral of e to the u is e to the u, right? So 1/3 e to the u plus c, which would be 1/3 e to the 3x plus c. Now, after you do enough of those, you realize if you just have x times a constant, you end up just dividing by that constant. But it's still a u substitution, okay? Now, what we're about to do is just like that, okay? But you have this extra step of 1 over the natural log of a. So if you have a base that's not e, say it's 2 to the x or 3 to the x, or in this case 4 to the x, okay, your base is something other than e, then you have this extra multiple here, or factor, of 1 over the natural log of a. And so again, that term is factor, not multiple, but we're going to multiply by 1 over the natural log of a. Alright, so let's try this. Alright, so I've got the integral of 4 to the negative x. So we know that the integral of 4 to the x is 4 to the negative x, but look, I don't have just x up there, right? I have a negative x, so I need to do a u substitution. So let's let u equal negative x. Alright, the derivative of that, or du, is negative 1 dx. Okay, now look at what we have. If I substitute now, I have the integral of 4 to the u. The problem is, what's left over, what hasn't been substituted for, is just dx. What do I need? I need a negative 1 dx. So how do I fix that? I throw a negative 1 inside and a negative 1 out front to compensate. So I need a negative 1 in front of here, or just a negative, and now I do have a du there. Now we use our rule above. So this integral is negative 1, and then it's going to be 1 over the natural log of a. Now our a in this problem is 4. It's our base, right? Times a to the x. Okay, so that's going to be times 4 to the u, because this is what we're integrating, plus c. And then I need to go back in and substitute what u is. So it's going to be negative 1 over the natural log of 4. Notice I didn't put the 1 there. That's fine. 4 to the negative x plus c. So that is my integral. All right, let's keep going. Look at this mess. Now what I want you to notice, first of all, what is your exponential part? So there's my exponential part. And I don't have just a plain x as my exponent, right? I have 3 minus x squared as my exponent. So what you need to do is, first of all, always attempt to let u be the exponent. And if it doesn't work out, then maybe there's a trick involved, or you can make some kind of adjustment, okay? Or you have to do it a completely different way. So right now I'm letting u be my exponent, 3 minus x squared. I need to take the derivative of that. So du is 2 times 3 minus x times negative 1 dx. I use the chain rule, which is equal to negative 2, 3 minus x. I forgot to reduce that by 1. That's to the first, right? Dx. Now when I look back at my problem, okay, the highlighted part, that's 7 to the u. All the rest of that needs to be my dx. Now look, I have Let's highlight this in aqua. 3 minus x dx. Down here, that's that part. So I'm clearly missing a negative 2. Can I just multiply by negative 2 inside? Sure I can. What I can't do is put a variable out front. We didn't. We just put a constant out front. So I'm okay. Now let's actually write down what we have. We have negative 1/2, the integral. All that highlighted in aqua there, along with the negative 2, that is du. The yellow part is 7 to the u power. Then I find that integral. So this is negative 1/2. All right. Now the rule says if I have 7 to the u, that's going to be 1 over the natural log of 7. Okay. And then I write 7 to the u. And don't forget your plus c. So when I simplify that, it's going to be, now watch this. This negative 1 times this 1 is negative 1 in the numerator, and this 2 I'm going to put right next to the natural log of 7. And it's going to be 7. Now we know what u is. Remember, it was 3 minus x squared plus c. And that is your final integral. Now for the last few examples, what I'd like to talk about are just some strange examples. A lot of it's about notation and just thinking through what you have in front of you. I know, first of all, with this problem I, the derivative, d over dx just means the derivative of e to the e power. Now my question to you is, where's the variable? E is not a variable. You don't want to use e as a variable ever, because it represents the irrational number of the natural base. Okay, so e to the e is just a constant. Matter of fact, you could type that in your calculator. I think I will, because I don't know what the value is right off the bat. So I have to hit second e to get the e as the base, and then I'm going to raise it to e, and then it still wants something in there for that exponent, but it's to the first. So e to the e is actually 15.154262224. So y'all, this is no different than taking the derivative of, now this is rounded, 15.15426, and I'm going to put dot, dot, dot. Now what is the derivative of a constant? It's just 0. So even though this looks intimidating, e to the e, right? It's just a number. It's just a constant, and the derivative of a constant is 0. Weird problem, huh? Another one I want you to think about is the derivative of e to the x. Now that's different. This has a variable in it. Y'all know the derivative of e to the x is just e to the x. Okay? And that's all there is to it. It's just e to the x. Now, look at this guy. This is the derivative of x to the e power. Now, this is like a polynomial, sort of. Your e up here is not a rational number. Matter of fact, it's not a whole number. So this is not truly a polynomial, but the power rule applies to this as well. As a matter of fact, I had that in this video right here. This is without proof, and I haven't shown this to you, but the power rule applies to real valued exponents as well. We learned that in the power rule way back then. That does not have to be a whole number. It doesn't even have to be a fraction. It could be positive numbers, negative numbers, fractions, or any real number. So in other words, something like x to the e is totally valid. And notice it's just the power rule. So that would be ex to the e minus 1. That's your derivative. So the derivative of x to the e is, again, pull the e in front just like we always have. Rewrite your variable base here to the e minus 1 power. Okay, so let's go back to where we were. There it is. So one more time, the derivative of x to the e, you're just using the power rule, is equal to e times x to the e minus 1 power. Next problem, how about the derivative of x to the x? Now that looks a whole lot like the derivative of e to the e, doesn't it? Except it doesn't, right? E to the e, those are both constants. X to the x is a variable, and I mentioned to you just a few minutes ago how you would handle that. Whenever you have a variable raised to a variable power, you must do what we call logarithmic differentiation. And so let's do that right now for this problem. So the first of all, I need to write it as maybe y equals x to the x power. Then I have to take the natural log of both sides. So the natural log of y is equal to the natural log of x to the x power. Now what can I do now? And this is key. I have to move that exponent in front. So now I have the natural log of y is equal to x times the natural log of x. Notice I haven't taken a derivative yet. All of that was just simplifying using logarithmic properties, okay? Now I'm ready to take the derivative. The derivative of natural log of y is 1 over y, but since I took the derivative of y with respect to x, I have to put times dy over dx. That's really the chain rule talking right there. Then I have to use the product rule here because I'm multiplying x times natural log of x. So first times derivative of the second, right? So first is x. The derivative of the second is 1 over x. Plus, now I do the second, which is natural log of x, times the derivative of the first, which is 1. Now I want to write this simplified. So I have 1 over y on the left, dy over dx, equals x over x, y'all, is just 1, plus the natural log of x. My next step is I'm supposed to multiply both sides by y because I have to get the dy over dx on one side by itself. So on the left, that does leave me with dy over dx because the y's cancel. On the right, that gives me y times 1 plus the natural log of x. Finally, I'm not supposed to leave a y and an x in my result. It should be all in terms of x if possible. And I know that y is x to the x power. So my final answer, x to the x times 1 plus the natural log of x. Right? And again, that's called logarithmic differentiation, and that's what you have to do if you have a power to a power. Finally, to wrap up this short video, just a note that I need to point out. It's a limit involving e. Basically, the limit is e. And this is the same expression, just written two different ways. If you evaluate the limit as x goes to infinity of 1 plus 1 over x to the x power, or you could find a common denominator for that, and that would give you x plus 1 over x to the x power. It gives you e. How do I know that? Well, there's a theorem, but let's check it out, right? So let's plug in, let's just try x equals 10 to start with. So that would be 1 plus 1/10 raised to the 10 power. Okay, I'm going to type that in my calculator. Of course, that's 1/10, so that'd be 1.1, right? 1.1 to the 10th power. And 1.1 raised to the 10th power gives me 2.59374246. So 2.593742, won't write every digit down. Now let's try plugging in 100, right? So it's 1 plus 1 over 100 to the 100th power. Well, you know 1 over 100 is 100th. So that when I add that to 1, that would be 1.01 to the 100th power. Let me tell you what I get. So 1.01, and then let's raise that thing to the 100th power, and I get 2.704813. Okay, and that keeps going. Let's try 1,000. That'd be 1 plus 1 over 1,000 to the 1,000 power. If I write that in decimal form, that's 1 plus 1 1,000th. So that's just 1 and 1 1,000th. So you remember tenths, hundredths, thousandths to the 1,000 power. Type that in my calculator. So 1.001 raised to the 1,000 power. And I get 2.716923. If I haven't bored you to tears, let's try it one more time because I have room. So it'd be 1 plus 1 over 10,000, right? To the 10,000 power. Just hang with me a minute. That's 1.001. Oops, I left out a 0. There we go, 3 of them. To the 10,000 power. When I type that in my calculator, 1.0001 raised to the 10,000 power. And I get 2.7184, 592, All right, now the question is what is e approximately? If I type in e to the first, that's what you'd have to type in your calculator. So I have to hit second and the natural log button, and I get 2.718281828. Now that makes it look like that continues to repeat. That pattern does not. It just is all that shows up on my calculator. So see, I've already got the 2.718 at 10,000. So if I plugged in 100,000, I would be even closer. So that's just a good limit to have in your mind. I don't have any examples involving that, just something I wanted to point out. Okay, I hope you have a wonderful day, and this wraps up the section about logarithms with base e.